Hi everyone, here we are in chapter 7. So hopefully you read the introduction to chapter 7 in the lecture before looking here. I will just kind of point you to some things and just try and not really summarize, but just say in a couple words what's happening. So it could be that the central limit theorem, maybe that makes sense to you, or maybe it still seems very strange and you're still trying to even start to wrap your head around it. So the YouTube link that I put there in the lecture, especially since we're not meeting in person, really recommend you go and watch that. It's called The Central Limit Theorem Clearly Explained. So a couple things about that video. For one, the guy who does it, he does several of these clearly explained YouTubes, and he's got kind of a personality. So he, I guess I'd say he's pretty like my definition of just like classic nerd, and just the way that he speaks, even, right? So, but he does a good job. If we were in class, I would play that YouTube for us, but I would only play these two parts. So, if you want to, watch the first 28 seconds and then really get into here. The video is a lot longer than that. You can certainly watch the whole thing. The more, the better. But if we were in class, I'd be playing you just this part. But maybe because you're not meeting, you might want to look at that a little bit more. There's probably some other really good YouTubes out there as well. The basic idea, just in a couple of sentences, we are going to look at distributions that might not be normally distributed like we were studying in chapter 6. It turns out that we can make non-normal distributions normal. What we do is, instead of taking the data to be the original data, we can take several samples. And if we take the averages of each of those samples, and we think of those averages as being the data, and we plot the averages of all of these samples, it actually turns out to be normally distributed, no matter what we start with. We might start with an exponential distribution. We might start with a uniform distribution. We might start with something that doesn't have a name. It's just all this random, this random curve that doesn't have a nice shape at all. It doesn't matter. If we take all of these samples, if we take a lot of samples and we just look at the averages of each one of those samples, and we think of the averages as the data values, then when we plot all of those averages, it's going to come out to this really nice bell shape, we say. It's going to look like the normal distribution. Okay, so that's kind of what I was trying to get at in those first couple of paragraphs, and what he'll explain in that video too. In the end, we come to this formula, and it looks very similar to the original formula for the z-score. Here, instead of x, we have x bar. We still have mu, so that carries over. We still have sigma, but now we divide sigma by the square root of n, and these are what all these things represent. Again, hopefully you read this already, but just trying to quickly summarize and maybe make it a little bit simpler. And oftentimes the second or third time that you hear something explained, it starts to click. So we've got our population mean is mu, our population standard deviation. Those are the same as in the original z-score. But now we're going to include our sample size. So it turns out if we have a big sample size, that's going to create a different bell shape than if we have a smaller sample size n. And now instead of x, we have x bar. Well, that still represents the sample mean, way back, all the way going back, all these things back to chapter 2. Okay, so let's get into the first practice problem, and I've got it here with me. And this first practice problem really starts to help us just see how problems are going to feel. So I've sort of laid this out here to get started, so I'll go ahead and read it. says the average age of a vehicle registered in the U.S. is 96 months, with a standard deviation of 16 months. However, the distribution of ages is unknown. A random sample of 36 vehicles is selected. Okay, so even before we get into part A, they're telling us some information. They're telling the average age of a vehicle in the U.S. is 96 months, so that's our population mean, right? All of the cars in the U.S., the average age is 96 months, which I think, how long is 96 months in years? I don't know. It's like 6 years, something like that. 5 years. Oh, 8 years. My mistake. Okay, I just crunched that out. 8 years. All right, that seems reasonable. The average age. I think my car is now 12 years old. Oh boy. Okay, so standard deviation is 16. All right. And the distribution of ages is unknown. We have no clue what the distribution of ages looks like. You know, probably a lot of people drive new cars. And it probably kind of drops down, but you know, there's a lot of old cars out there too, like mine, or much older. So who knows what the distribution, what the curve looks like. And then, let's see, okay, a random sample of 36, so n is 36. All right, that's everything. Then we get into part A. Find the probability that the mean age of a sample is less than 100 months. Okay, well, the last piece of information we need, of course, is X bar, and that's the 100. What's up with that? Okay, so remember, X bar is a sample mean, and that's what they tell us. The mean age of a sample is less than 100. So we're gonna take our X bar to be that mean sample of 100. And we're going to go through, at this point, really very, very familiar steps like we did in Chapter 6 to find this probability. So we're going to use our now altered, adjusted formula for the central limit theorem, but we're still going to use the table of z-scores, the same table that we used in Chapter 6. So here we go. Let's plug all these values in, and I'm just going to get right to the point with this one. So I'm plugging in my X bar minus mu over sigma, and sigma is divided by the square root of n. Be sure in your calculator that if you were to just go for it right here, which you certainly can, plugging all that in, be sure that you put parentheses around your numerator and your denominator. If you've got a more modern calculator, you might have this nice display, but if it's a slightly older, definitely use parentheses, or you might simplify it a little bit first. Maybe just go ahead and do that subtraction, go ahead and take that square root. You would still need the parentheses there. In any case, make sure that when you crunch these numbers you get 1.5. Then you know you're doing it right. Okay, so hey, we have our z-score, slightly new formula now. But from here, it's exactly the same as Chapter 6. We are going to find the probability that capital Z is less than the z-score we just found. Okay, practice number 1 is really as simple as it gets, right? It even says find the probability that the mean age is less than 100, and that's exactly what our Z table will tell us. It's always a less than. Okay, so at this point, hopefully you printed that table of z-scores, the two sheets. If you weren't able to do that, then go back into the Chapter 6 lecture. The last couple pages kind of have that, available for yourself while we're going through these problems together. So I'm going to grab mine, and I'm going to go to the positive z-score side, and I'm going to look up 1.50 0.9332, and that is my answer. The probability that the average age of a sample is less than 100 months is 9.9332, over 93% chance of that happening. You're like, wow, that's a really high likelihood. Now this, you may kind of reflect on this just for a moment before we get to part B. The average age of a vehicle is 96 months. Okay, we sample 36 vehicles, and we ask, what are the chances that the average of those 36 is less than 100? And it's super high. Like, wow, this seems like maybe for a moment that seems like maybe it's too high. You know, I take the average of my sample, and I mean, 100 isn't that much higher than 96, only 4 months. I mean, really? I mean, if I just stray 4 months above the average, it's over 90%, well over 90%. Here's why. We took 36 vehicles in our sample, okay? That's a lot of cars. Now, some of these cars are going to be a lot younger than 96 months, right? Maybe within 1 year. There's going to be several cars here that are probably less than a year old, or definitely less than 2 or 3 years old, for sure, in our sample. But then there's also going to be several cars that are quite a bit older. You know, 12 years old, 20 years old, right? So the new cars are going to be balanced out really well by the older cars. And so even to get the average up to be at 100 is very difficult, 100 months. So the chances that we still get something less than 100 months as the average of our 36 is really high. Because we're taking quite a few cars, there's going to be this balance. Okay, let's move on to part B. I've got that on the next page here. So part B, you know, it's really just a different value of x bar, but I do that for a reason. And that's kind of this thinking and starting to wrap our head around what the central limit theorem does probability-wise. Part B says, find the probability that the mean age of the sample is less than 105 months. Okay, so of course we'll take x bar now to be 105. And just kind of based on that conversation a moment ago, it was over 93% just to get the average up to 100. What's going to happen if we tack on another 5 months? Okay, let's see. Well, at this point, you know, we can plug all these numbers in, and I'm just going to go for it here. So we'll put in the 105 now. All the rest are the same. We still have mu is 96, sigma, n. They're still all the same values. If you were to go for it here, be sure to use parentheses on your numerator and denominator. Maybe you decide to clean this up slightly, do some of those easier calculations, and then divide. Be sure to use parentheses here. Whatever you do, confirm that your calculator will give you 3.375. And I'm just going to do that again myself. 3.375, okay. Since this is a z-score, and we're using our tables, we have to round that. We have to round it to 2 decimals because that's what our table provides. Okay, so we want to think of this as 3.38. Then, really, same idea. We're going to check out our table. Again, it's a less than, probability less than, and we're going to look up 3.38. Okay, so if you've got your table, again, it's a positive. 3.3 is almost at the very bottom, and 3.38 is the second to last. 0.9996. Wow. There's our answer. It's barely shy of 100%. 99.96% chance that your sample of 36 cars has an average age less than 105 months. That's not even a year above the average age of all the cars in the US, 96 months. It's only 9 months higher. Yet, if you take 36 cars, because the new ones are going to balance out with the old ones, and there's going to be a lot probably right around that 8-year mark, to stray all the way up to make that average over 105, very, very, very unlikely. Now that is, these percentages are way higher than we'd probably guess on our own. But it's because we're taking an average of 36 cars, and 36 is a good number. Okay, so just visually what's happening, and again, this is like we're getting used to the formula and the thing and just the concept. So I'm really like diving in deep here to the concept side. So I've graphed just a rough sketch of what the central limit theorem does. Graphically, right, the original normal distribution, it's pretty tame. The original normal distribution kind of comes up and it's got this gentle bell shape, got this kind of nice, easy kind of graph. It's not real extreme. The central limit theorem pushes the data to the center and it pushes it up at the same time. So when you take your data to be the sample averages, it really just presses all that toward the middle. So as you go out, even though it might not seem like you're straying very far away, it's actually, you're moving quite past a lot of the data. And this probably isn't even quite accurate. It should probably be even more extreme in the graph, but just the way we've drawn it. So at 100, right, the amount of data below that was what, 93.32% or something like that. And then to get all the way out to 105, like how drastically that drops, that's well over 99% of the data is less than 105. So we get this pushing. Okay, I think I've made my point. That is practice number 1. I'll see you in the next video.